is Islam Ashraf. He is co-founder and CTO of ASA Microsystem Inc.
Okay. So can you hear me? Hello. Hello.
Hello.
Hello. Yeah, can you
Okay.
hear me now? Yeah.
Yes. Okay. Okay. Next presentation. Our next presenter is Islam Asraf. Okay. Our next presentation title is ASA RISC V processor optimized for edge AI ML security and smart IoT sensors. Okay. Can you
Thank you.
share your presentation? Okay.
Yeah, I'm trying to share my presentation.
Okay.
Yeah, but I did not get the share button yet. Okay, now I got the share button. Yeah. So
Okay. I can see your present. Can see your slide.
okay, thank you so much. So thank you everybody for joining this session. So today I like to describe about Asa Micro's ultra low power IoT and AI edge computing platform optimized for edge AI, machine learning, and a smart IoT. So first of all, I would like to discuss about Asa Microsystem. We have founded in 2018, and we was we are still a startup and working on the research and development. Our headquarters is USA, but our R&D office in Japan, and I'm also living in Japan. And as from the title, I already mentioned that we are focusing on next generation AI edge inferencing product development for the edge, not for the high performance, but for the edge devices. So our value proposition is since we are talking about edge, so we are concerned about the power, we are concerned about the battery life. So we are developing ultra low power, high performance RISC-V based processors and vector accelerators to make a smart IoT and edge AI computing for cost and time to practical market reality. Our target markets are essentially medical, industrial robotics, a smart camera, a smart appliance, a smart sensor, drones, and consumer products. Next, I would like to introduce the ASA RISC-V processors that we are working on. For that, I would like to discuss why ASA RISC-V processors. Of course, you know that RISC-V is an instruction set independent of processor architecture and implementation. So it is the architecture, instruction set only. Architecture can be commercial or open. And commercial RISC-V processors have their own proprietary microarchitecture for the same instruction set. So as far our understanding, majority of RTL is generated from chisel-based implementation for RISC-V processor. So our own proprietary patent pending microarchitecture that implements the same RISC-V ISA in Verilog. And our implementation is lower in gate count, smaller in die size, and also low power. And the same code is scalar in clock rate. I mean, you can implement the same code for 100 megahertz to gigahertz, depending on the options. So this is the 32-bit processor family, we have not planned to develop many code. So the first one, AR32Z, is a scalar code, and it is now ready for evaluation. And we are also have developed the FPGA development platform for prototyping. And as another one is AR32E, which is superscalar processor with multiple parallel executions. This is also a smallest footprint at its given architecture for the superscalar. And of course, all of these are depending on the computational requirements. You can select a scalar or superscalar. And the last one is 128B. This is the vector processor. So we can see that vector processor can be worked as an accelerator for many applications like AI, vision processing, image processing, and so on. Since AR32Z and E does not have the vector extensions, but still it has the opportunity to integrate the SIMD, MAC, or custom DSP coprocessor to meet the customers' requirements on the edge computation. So this is the RISC V based technology portfolio. Of course, center is our RISC V processors implementation, and based on that, we like to provide different kinds of solutions to the customer. For example, system on chips for your custom requirements. Of course, we have a for the designing an SoC. Most common blocks are interconnect, AXI or HB memory, wrappers, DDR controllers, SPI, SQC UART. So we have all of these IPs there, and we can build an SoC at a very short time. And we have different kinds of AI accelerators we will discuss later. Of course, we can license the processor as it is, and we can implement the custom processors according to the customer's requirements. And we are also working on for the chiplet and multiple solution and the vector processor. So all of these solutions, we think that two things is important at the first time is having a simulator so that we can simulate what we are doing. Is we can play around it and we can check that our idea is correct or wrong. Can we are we going in the right direction or wrong? And another is, okay, we have developed our RTL, so without going for the costly ASIC implementation, can we do a shorter FPGA rapid prototyping? So in this case, all of our cores are FPGA can do. We by ourselves we provide the FPGA prototypes and also the development boards, and we are based on the open source software tools. We do not have we do not want to lean ourselves for any custom compiler development or something. So this is our first development board we have already done. It's of course we are going to add many more IPs very soon, but until now we have this implemented in RTX 700T device, and this full SoC was running at 100 megahertz, which contains UART, I2C, GPT, ROM, and also 2S RAM as a program and data memory. The full SoC requires only 3,500 LUT. Among them, including AHB, the AR32Z processor requires 1,726 and core requires 1,464. And we measured the dynamic power in Vivado using the BCD files, and we got the dynamic power of 7 milliwatt for the core. And then we prepared another SoC for using the Xilinx MicroBlaze processor for equivalent microcontroller configurations and connecting all the same IPs Then we got that dynamic power in FPGA is also lower than microblaze or IR32Z. So almost 77% less power than microblaze. And to make sure, we also measured the board power using the Agilent ammeter, which also give the equivalent difference. And we also have do the synthesis and place and route using the TSMC 14 nanometer LP, the standard library from Dolphin, and this synthesis and PNL is based on 6-track library. And this is we selected the frequency 350 megahertz, but in the given 6-track library, we can go up to 800 megahertz as well. And the macro dimension is like this. And the important thing is that standard cell utilization is very low compared to 11,369, and flip-flop is 1,685. As you know that RISC V specifications requires at least 32-bit general purpose register. So this register file is implemented using a flip-flop. So almost there are around 930 flip-flops for the register file. So the rest of the flip-flop are for the pipelines. And the standard cell utilization was 82%. So as you can see that the power is, leakage power is very low, and dynamic power is around 2.4 milliwatts. So we divided by the frequency and we got the dynamic power 6.9 microwatt per megahertz for given 350 megahertz, and voltage was 1.1 volt at typical condition. And this is the AR32Z. What we like to do in the next step is connecting tightly coupled accelerator to the processor core. So that we already know that the tightly coupled data memory is already there, but we like to go one step further, in which that processor, memory, and accelerator will form a triangle to do having a low latency access each of them. So the benefit is that this interface also contains the ASUS proprietary channel interface, which also have the indication or hints for the clock domain, power gating, also other features for the controlling the dynamic powers. As a result, so there is a possibility that we can provide the full accelerator plus processor at a lower power. And accelerators can be ASA or can be third-party developers, as long as they meet our interface requirements. It is good enough to connect any third-party accelerators, or even any accelerators written in C++, and we can do the high-level synthesis as well. And the accelerators can range from DSP to AI inferencing, such as image processing, audio processing, DSP, and many more. This is another, as we mentioned before, that we have our own simulator, ARSim, which is we have a long connections to C++. So we have our own C++ based simulators. Mean we have the model library for the processors, peripherals, bus, everything in a C or C++, and we plug in into our simulator, so that we can simulate not only it is not an instruction set simulator, not only just a single process. We are talking about the simulating the whole SoC, the whole system, how it's going to interact with others. And also we can, if some customers or someone wants to simulate the whole not only whole SoC plus also PCB. In PCB they want to connect some third party, of course, for example, Wi-Fi, Bluetooth, or ADC, DAC, flash, or anything else. Then if they come up with the models for those devices, then we can simulate not only SoC but also including the device connected to the PCB. And we are working on to develop the RTL to C++ conversion. So if maybe all the customers do not have for their own proprietary IPs does not have the C++ model, so that we can translate it and simulate it, plug into the ARSIM for the simulation. And we are also working on how this ARSIM can work together with the high-level synthesis tool, so that in future we can not only the simulation but also do the FPGA prototyping at the same time. And another feature of the ARSIM is we know that most of the traditional RTL simulators used in the industry, like Model Sim, Incisive, and others. So we can connect the ARSIM to the EDA tools. Already we have connected this ARSIM to Model Sim, Mentor Graphics Model Sim, and also the Vivato FPGA EDA tools, Vivato, and it's working fine. So we can work for the verification as well using the ARSIM, because ARSIM worked as a golden model, so we can check. So this is our processors roadmap. Right now we are here. Of course, we are supposed to deliver the AR32E, but due to the pandemic situation, so we are a little bit slow. But we are working on the Xenon, the FPGA-based SoC products that we mentioned, that we are deliver the development board so that anyone can play with our processors, not only processor but also the SoC. And we are targeting to deliver the real-time operating system included in the FPGA board, so maybe they do not have to worry much about how to write the programs. And AR128B our vector processor, and then we are planning to develop a 4-processor cluster, which could be 4 AR32Z or 4 AR32E. And then we would like to develop the AR128B vision processor, which will contain the multiple vector processors. And at the same time, as we have mentioned, that we are working on the chiplet. So this is PCI Express based, multiple chips connected on a package, system in package. So like this, we are working on it. And right now we are developing the simulators for the chiplet. So before making a full chiplet, now we can provide the concepts to simulations and modeling. So the ASA, since for the age, AI is also becoming a hot topics. So in that case, ASA is providing the AI solutions from 3 different perspectives. First of all, the tightly coupled with ASA processor, the accelerators, custom accelerators. The benefits is low power, low latency, and complete FPGA solutions will be available. And vector processor, I think I do not need to say about the RISC-V vector processor. It has a lot of advantages, we already know. And the vector processor, we would like to implement the vector processor for the FPGA at highest maximum operating frequency as much we can. And for the multi-core, our multi-core approach is that we can have the chiplet solutions, the one which the multiple processor will be talk to each other through the PCI fabric or some others. And this would be suitable for in future 5G applications as well. So our engagement objective is that seeking the strategic partners to accelerate business success. Like we are looking for key partnership on the foundry and chiplet packaging, and also access to essential IP and development tools. If someone needs, for an example, if someone needs a totally custom processor for their own purpose, then we can support not only delivering the processor RTL, but also the simulator. Of course, not only instruction set simulator, but a full SoC system simulator. So thank you very much. Hello.
Okay. じゃあ変わりますか。Well, thank you, Asha, and for your presentation. Do we have a question here? Let's see.